Every AI agent needs a brain, and that brain is a language model. Here we look at how that model actually gets trained to become useful, how raw text turns into something that can follow instructions, reason, and use tools. Two ideas will come up again and again. First, when we hold the task, the model, and the training budget constant, supervised fine-tuning tends to memorize the exact examples it's shown, while reinforcement learning tends to find strategies that hold up in new situations. Second, and this is the more surprising one, the quality of your training data and your practice environment matters far more than which algorithm you choose. Model capability builds in 3 stages. Pre-training is like reading 10,000 books. It builds broad knowledge but doesn't teach the model how to be helpful. Supervised fine-tuning is like a teacher walking through worked examples, fast, cheap, and it teaches format and style. Reinforcement learning is like solving problems yourself and learning from what works and what doesn't. Expensive, but capable of discovering solutions nobody ever demonstrated. At its core, a language model learns by predicting the next word in a sequence, over and over, across trillions of examples. Each prediction is compared to the real next word, and the model adjusts itself to get closer next time. Do this enough, and the model absorbs grammar, facts, and reasoning patterns. There's no shortcut to getting that many predictions right. But right out of this stage, the model isn't very helpful yet. Ask it a question, and it might just generate more questions, because that's a pattern it saw a lot in raw text. Fine-tuning uses the exact same underlying math as the first training stage, still just predicting the next word. What changes is the data. Instead of raw text, the model sees carefully written question and answer pairs. And there's one more trick. The model is only graded on the answer part, not the question part, so it learns how to respond rather than how to ask. Because the goal is to reproduce these exact answers, this stage is very sample efficient. A few thousand examples can lock in a format. The trade-off is that it can memorize the surface pattern of those examples rather than the deeper task. Reinforcement learning needs to be able to judge whether an output succeeded or failed. And if the output is a garbled mess, there's nothing to judge. So fine-tuning often comes first, purely to stabilize the output format. Once the format is reliable, reinforcement learning can refine the actual strategy. This matters most for smaller models with strict output requirements. Some very strong models can skip straight to reinforcement learning and develop good reasoning on their own. But even then, teams often add a short fine-tuning pass afterward just to clean up readability. Here's the core comparison. Fine-tuning maximizes the probability of reproducing a specific labeled answer. Reinforcement learning maximizes expected reward across many attempts. Fine-tuning is highly sample efficient. A few thousand examples can be enough, but it depends heavily on how well those examples cover real-world variation. Reinforcement learning needs far more data and is less stable to train, but it can generalize better when the reward signal genuinely reflects what you care about. Use fine-tuning to lock in format and style. Reach for reinforcement learning when you need real generalization. There's a subtler pattern underneath this. Fine-tuning, because it's trying to match probability across all the examples it saw, tends to spread its confidence across every reasonable answer in the training data. Reinforcement learning tends to concentrate probability on just the handful of behaviors that earn the highest reward. Neither tendency is absolute. It depends heavily on the data and how the training is set up, but it's a useful mental model for why the two methods behave differently. Why does trial and error training sometimes find things imitation never could? 3 reasons. It can recognize and reward entirely new behaviors that were never demonstrated, as long as the reward function can score them. It can take advantage of tasks where checking an answer is much easier than producing one. Grading a math problem is far simpler than solving it, and it trains on situations the model itself actually wanders into, which avoids a classic failure mode where a small, early mistake spirals out of control because nothing ever showed the model how to recover. Stepping back to the fundamentals, in classic reinforcement learning, an agent observes its current situation, takes an action, and the environment responds with a reward and a new situation. And this repeats. Different systems have very different action spaces. A newborn animal learning to balance has continuous muscle movements. A chess player has a fixed set of legal moves. A modern AI agent, by contrast, can generate open-ended sequences of words and tool calls, a vastly larger and messier space of possible actions. One of the foundational algorithms here is Q-learning. It asks a simple question: if I take this action right now and then act optimally from then on, how much total reward can I expect? Each attempt nudges the estimate a little closer to what actually happened. It's elegant and well understood, but as the next example shows, it needs an enormous number of attempts to work. In a hidden mechanism puzzle game, with an 11-step optimal solution, an agent trained purely through trial and error needed about 10,000 full attempts before it reliably solved the puzzle. In a simulator, that only takes about 10 seconds of computer time. But translate that into a real-world task, where every action has a cost or a consequence, and 10,000 attempts is simply not realistic. Now compare that to a language model-based agent given the exact same puzzle, with no prior training on this specific game. It solved it in 18 steps on its very first attempt. Its reasoning was visibly purposeful, recognizing that a weapon beats bare hands, realizing a locked door means it needs a key, and combining items intentionally. The trial and error learner has no concept of what a key or a door actually means. It can only rediscover those relationships through raw repetition. The language model isn't running a smarter learning algorithm. It's carrying enormous prior knowledge into the task from the start. There's a genuine shift in thinking worth knowing about. Researchers first believed better algorithms were the key to capable agents. Then focus shifted to building better training environments. Eventually, it became clear that the single biggest lever was something else entirely: the broad knowledge baked in during initial language training, which has nothing to do with reinforcement learning at all. The real order of importance turned out to be prior knowledge first, environment second, algorithm third. A few quick technical notes on foundational training. Training a small model completely from scratch can be done cheaply and quickly with the right algorithmic choices. Sometimes just hours and a modest budget, if you pick good optimization techniques. Teaching a model to understand images typically works by freezing a pre-trained vision system, training a small connector layer to translate between vision and language, and only then fine-tuning the whole thing together. And teaching a model a new language is far cheaper if you build on an existing model rather than starting over, though you need to mix in some of the original language too, or the model forgets what it already knew. Where does high-quality training data actually come from? Three main sources, usually combined. Human experts write a small set of gold standard examples first, to nail down the exact format and tone you want. A strong existing model then generates much larger volumes of similar examples, which get filtered for quality. And finally, the model can generate many candidate answers to the same question. Keep only the ones a checker confirms are correct and train on those. The discipline of filtering and deduplicating matters more than raw volume. A few thousand clean examples consistently beat 100,000 messy ones. A few concrete examples of what fine-tuning actually locks in. For voice generation, it can capture not just a specific voice, but expressive habits like laughter and sighs. For reasoning, a model trained to think in a handful of languages can, surprisingly, generalized to reasoning fluently in a language it was never explicitly trained to reason in, because that cross-language ability was already latent from earlier training, and fine-tuning simply activates it. And for efficiency, you can compress an expensive process, a long instruction plus lengthy step-by-step reasoning, into a fast model that produces the same quality answer directly, without needing all that overhead at inference time. One practical caution: training a smaller model to imitate a stronger one is technically ordinary fine-tuning, but some AI systems are cautious about helping build a full pipeline for this, treating it as sensitive. The good news is you rarely need to target the very best model available. Your source model just needs to be clearly stronger than the one you're training, not the best in the world. Putting this into an actual decision process. First, ask whether training is even necessary. Often, better prompts and better tool design solve the problem without touching the model at all. If training genuinely is needed, start with fine-tuning. It's cheap, fast, and excellent for nailing down format and consistency. Only escalate to reinforcement learning when you specifically need the model to handle situations your examples don't cover, or when demonstrating every possible case would be too expensive. And if your model's output isn't reliably well formatted yet, fix that with fine-tuning first. Reinforcement learning can't learn from a signal it can't even read. Now consider the simplest possible reinforcement learning setup. One input, one output, one reward. No multi-step complexity. The basic idea is to generate several different responses to the same prompt, then nudge the model toward whichever one scored highest. One common method adds a safety clamp, so no single update swings the model too far in one step. Another skips the extra scoring network entirely and just compares several responses to each other directly, which is simpler and cheaper to run. Reasoning models often overthink easy problems, generating long chains of reasoning when a direct answer would do just as well. One technique trains the model to actively choose whether to reason step by step or answer immediately, based on how hard the question actually is. In practice, this held accuracy steady or slightly improved it, while cutting response length by roughly half to two-thirds on easier benchmarks, a real efficiency win without sacrificing quality. Here's a controlled test of memorization versus generalization. In an arithmetic card game, training used one specific rule, and testing then shifted that rule, plus changed some visual details the model had never seen in that combination before. Under the rule shift, the imitation-trained model actually performed worse than before training at all, because it had locked onto the specific pattern it was shown. The reward-trained model, by contrast, improved, because it had learned to actually recompute the answer rather than memorize one fixed mapping. Under the visual shift, the reward-trained model improved dramatically, while the imitation-trained model got noticeably worse. It's worth noting the reward-based training only worked this well because a short imitation phase had already stabilized the output format beforehand. Where does natural, high-quality conversational behavior actually come from? A three-stage process. First, a base model is fine-tuned on demonstrations to follow instructions. Second, human reviewers compare pairs of responses and say which one they prefer. This is much easier and more reliable to label than giving an absolute quality score. That preference data trains a separate scoring model. Third, the original model is further trained to produce responses that score highly according to that learned scorer. There's an important safeguard in this process. The model is penalized for drifting too far from where it started. This matters because the scoring model was only trained on outputs similar to the starting point. Push far enough away and its scores stop meaning anything. This safeguard prevents two failure modes: the model learning to game the scorer without actually getting better, and the model's output degrading into repetitive or incoherent text. In fact, Research has shown that a learned scorer's rating can keep climbing throughout training, even as real human-judged quality peaks and then quietly declines. The model has learned to flatter the scorer rather than genuinely improve. There's a simpler alternative to training a separate scoring model. Given pairs of preferred and rejected responses, you can train the model directly on a straightforward comparison loss. No separate scorer, no extra sampling step needed. It's about as simple to run as ordinary fine-tuning. The trade-off is that it only ever learns from the exact preference examples you give it. It can't explore new behavior beyond that data, so its ceiling is set entirely by how good and how broad that data is. A quick comparison of training approaches. One method uses a value estimating helper network and works well for long, multi-step tasks. Another skips that helper network, comparing several responses to each other directly, well suited to short, single-step tasks with a clear reward. Two other methods work entirely offline from existing preference data, without needing to generate new responses during training. Good, when you already have quality comparison data on hand. And a simple inference time trick is to generate several candidate answers and just pick the best one, without changing the model at all. A fast way to get a quality boost with zero training. In practice, any well-implemented version of these will get the job done. The real differentiator is rarely which one you pick. Here is the idea worth remembering most. The real hierarchy of what matters is the model's starting knowledge first, the realism of the practice environment second, and the specific algorithm a distant third. If your simulated practice environment doesn't resemble the real deployment, for example, a scripted customer service simulation whose error messages never match production, the trained model will learn a strategy that only works in the simulation and falls apart the moment it ships. This is the single most common reason these training efforts fail, and it's almost never the algorithm's fault. Building a genuinely faithful practice environment is often harder and more expensive than the training run itself. The algorithms, meanwhile, are largely standardized and easy to plug in. Put your effort into the practice ground and the data. That's where success actually gets decided. To bring it all together, fine-tuning and initial language training share the same underlying mechanism. Fine-tuning just changes the data and narrows what gets graded. Use fine-tuning to lock in format and consistency cheaply. Reach for reinforcement learning when you genuinely need generalization, but only once your reward signal and practice environment are trustworthy. The memorization versus generalization pattern we saw is real but not universal. It depends entirely on how the data and reward are built. Conversational polish and safety typically come from human preference training, while step-by-step reasoning and tool use typically come from verifiable reward training. Real systems use both together, and above everything else, the deciding factor is almost never the algorithm. It's whether the practice environment and the training data actually reflect the real task.